Welcome to today's session. The problem statement that we're going to discuss is dynamics in the era of AI or perhaps in the era of LLMs, right? So the one of the major problem statements with today is there was a complete era of machine learning, static system, software engineering, right? And the one of the fundamental problems with all of these systems combined is staticness, right? Everything needs to be the whole debate around being you know something which is stochastic or something which is deterministic, right? And the argument that's always given is that the software engineering has always been deterministic approach. API needs some pretty well defined structured output, needs to have ML system require features to be there. There are features that machine learning works, that there are sets of features, and based on sets of features, based on the pattern, the final equations or perhaps the determination is made. All of these are statics, right? But the real world don't function this way, right? The real world is dynamic, is filled with noise, and hence to bridge this tech gap. And I'm going to a completely new era of technology here, where we am saying that all the systems can be context aware. Everything can follow a kind of a deterministic approach, or perhaps sorry, everything can follow generative AI based approach or context aware approach, where there's no one size that fits all, and that's a fundamental argument around all of these things. Fixed feature engineering, pipeline, single model, static use across all contexts. So if you look at kind of today, the scenario is that if I want to build a particular system, let's assume that I want to build a payment gateway, what I'll do, I'll build sets of APIs, I'll define the sets of APIs. Okay, this should be the input, this opener. I'll spend months around that. And I'll be spending months around, experimenting with different architecture and finally selecting this one architecture that would work, well for my use case. And turns out that couple of months later, when it's there in production, it never works out for me. That works for everything. Context aware LLM or perhaps engine comes here and that says that you give decision making skills to each part of your neurons. You give decision making skills to each junction point or perhaps every part of your pipeline, where you say that based on this current regime or based on this current understanding, this is what the architecture works well. It automatically does the decision making instead of following one decided static architecture. Decides based on the context. It decides, okay, this is the architecture that works well. I'm going to go with this based on these conditions. This is what works well. I'm going to shift between these two architectures. It makes the API call also a little dynamic. It makes everything little dynamic. So it says that, okay, this is what I used to hit this particular API. Now I'm going to go with this particular sets of API sets. Basically, how a system like this would function, right? The way system like this would function is we will highly depend on the contextual signals, will not depend upon a very single static value, will depend on contextual signals. When I say contextual signals, it means that what is the, kind of, when you're talking in terms of software engineering, it would depend on the logs, it would depend on the context situation, what the user, instead of, kind of a very, and it's still very unexplored. This does not have, a lot of exploration done on it as of yet. They're still very unexplored. But if you look at from this perspective, it would be there are series of context, there are series of laws and all of that stuff. And based on that context, the LLM is trying to make a decision, may perhaps kind of an intelligent AI system execution strategy that this is how I'm going to execute instead of following this one predetermined input output set. I'm going to have a variety in input and output set. Based on different inputs, I'm going to set different sets of output. So, doing a very quick comparison on Chronos and XGBoost. XGBoost is kind of, a lot of time series models, or perhaps is called as the queen that shall reign the algorithms of machine learning, XGBoost, and this is where Chronos strengths are compared to XGBoost strength. Meanwhile, feature engineering, the model can adapt really, really quickly to different seasons, seasonality data, to different regime shifts. Benefit for long range dependency is useful when you need zero shot or rapid deployment across many series, right? When you want to use the same model across, perhaps different areas, different. The Chronos can really help. Also, it is prognostic output supporting planning and risk sensitive decision. XGBoost and excellent when you have rich Tableau, COVID, promotion, weather, holidays, macro drivers, fast, cheaper, and often easier to explain to stakeholder. Cost is one thing that we have not compared things as of now. Kronos definitely would be costlier because it works on a token base. So you basically are passing each part as a separate token, and that is predicting. So if it's a huge the token cost for the token would be really expensive for us. And also if we are you know there would always be a limit to a context window. So those are the two where Kronos is definitely gonna lack, that is cost. And second is the context window, that it can't take your 5 years or 6 years of data. It can perhaps only take 3 years of data at max. This is what we can say when a feature table extends to what 100 200 features or even less than that kind of stuff. So this is what an enterprise deployment architecture looks like, where you have different data sources when streaming batches there. You have done some sort of scaling across the data processing, kind of stuff. Kronos service, pre-trained model plus model registry, forecast APIs, apps, decision, and all of those trends. High value cases for Kronos. Cases where simple model can win when many series across units were purchased too costly, seasonal or trend rate signals with the long range dependencies. Yeah, perfectly when the exact use case for a Kronos is where you have different model across spanning across different regimes, different seasonality, different countries, all of those things. This is where Kronos can add a high value seasonal or trend rate signals with long range dependencies. Rapid prototyping when the feature engineering pipelines do not yet exist. Risk aware planning approach that benefit from mentor than scenario forecast. Cases where simpler models can win short horizon problems with strong tabular features at a stable operating regime. Application with strict latency or infrastructure cost limits. Cost is where simpler models can easily win when there is only one smaller problem, particular problem set that one needs to solve. Use case requiring high interpreting for audit or regulator workloads. Very stable series where native ETS or reservoir audit perform sufficiently well. Kronos is most compelling and when the forecasting is complex, repeated, and expensive to handcraft. Exactly. This is the exact place where Kronos models like Kronos adds huge value when the model shines on complex data sets where forecasting is really complex, when the data regime shifts happens too many times, when you have to use the same model across 10 different countries and all of those things. This is where model like Kronos adds a huge value. That's a that's a simple trade-off where this can adapt really quickly across different regime and all of that stuff. But the moment there's a cost restriction or there's a huge context window, the simpler and models like XGBoost easily win. So final recommendation: keep Kronos the advanced forecasting layer. Use XGBoost as classic models selectively where simplicity, speed, or interpreting matters.